All right, today we're going to do the IGCSE from Cambridge International Examinations, Paper 6, which is the alternative to the practical exam for chemistry. And this is from May-June 2018, and the code is 0620/61. Okay, let's get started.
Yeah, let's do it. I'm pumped.
Question 1. The volume of dilute nitric acid that reacts with 25.0 centimeters cubed of aqueous potassium hydroxide can be found by titration using the apparatus shown. Okay, so complete the box to name the apparatus. Okay, so this little pipe thing with a stopper that opens and closes, and you could take out one drop at a time, it's called a burette. All right. B. Name a suitable indicator that could be used. Okay, so there's a few things you can use. You could use methyl orange, phenolphthalein, litmus. Any of those would work. Let's say methyl orange. All right. One answer you couldn't put in there, though, is universal indicator. You just don't use it during titrations. Okay, good. A student did the titration 4 times and recorded the following results. Okay, they had 4 different titration numbers, and the volume of dilute nitric acid used was recorded. So which one of the results is anomalous? Okay, so if we look at this, 18.1, 18.9, 18.3, and 18.2, the one that's clearly farthest away from the others is, you say number 2, titration 2, or you could say 18.9. It doesn't matter. 18.9, and that's titration 2. Okay. All right. C2, suggest what might have caused this result to be anomalous. Okay, so generally, what will often make you have more dilute nitric acid used is that you just overshot the endpoint. It's very difficult to get the exact drop you need. Okay, it's a skill. Okay, so it's very easy to overshoot. That's why you need to do lots of titrations. Another thing that you could put down here is you could say that you used more than the 25 centimeters cubed of potassium hydroxide that you were supposed to use. Okay, and C3, use the other results to calculate the average volume of dilute nitric acid that reacted with the aqueous potassium hydroxide. Okay, so to calculate an average, we take 18.1 plus 18.3 plus 18.2. You divide it by, there's 3 numbers in there, and the answer you get is 18.2 centimeters cubed, and you have to put the units in there because it's a volume. All right, it does say the other result, so don't include the anomalous one. Okay, good. D, the equation for the reaction taking place in the titration is shown. So we have HNO3 plus KOH produces KNO3 plus H2O. So the student concluded that the aqueous potassium hydroxide, KOH, was more concentrated than the dilute nitric acid, that's HNO3. Explain whether or not the student's conclusion was correct. Okay, so first of all, we have to look at the volumes that were used. That's the most important thing. Okay, so for this, we had an average of 18.2 centimeters cubed nitric acid was used. And that managed to neutralize 25 centimeters cubed of potassium hydroxide. That means that 18.2, the nitric acid was stronger than the potassium hydroxide. Okay, so the student said the potassium hydroxide was stronger, more concentrated, so that was incorrect. So the student was wrong because the nitric acid is more concentrated than the potassium hydroxide. And you know that because there was a smaller volume of nitric acid than potassium hydroxide in this neutralization reaction. So the nitric acid is more concentrated than the KOH, and a smaller volume of acid was needed compared to the alkali. Okay, so that's 2 marks. 1 mark is saying which one is more concentrated, and the other one is saying how do you know. Okay. Okay, so this is a long description, so it's good to highlight as you go along. So experiment 1, a large measuring cylinder was used to pour 50 centimeters cubed of aqueous sodium thiosulfate into a 250 centimeter cubed conical flask. The conical flask was placed on a printed sheet of paper, and then 10 centimeters cubed of dilute hydrochloric acid was added to the solution in the conical flask. A timer was started immediately and the mixture was swirled. The time taken for the printed words to disappear from view was measured. Okay? Experiment 2. The large measuring cylinder was used to pour 40 centimeters cubed of aqueous sodium thiosulfate into a conical flask, followed by 10 centimeters cubed of distilled water. Okay, so it still adds up to 50 centimeters cubed. This one's just less concentrated. The conical flask was placed on a printed sheet of paper. Okay, so it's still the same size conical flask because they haven't specified any change. So 10 centimeters cubed of dilute hydrochloric acid was added to the solution in the conical flask, which is exactly the same as the first one, and the timer was started immediately and the mixture was swirled. The time taken for the printed words to disappear from view was measured. So that's exactly the same, except the sodium thiosulfate is more dilute. All right, so experiment 3. Experiment 2 was repeated using 35 centimeters cubed of aqueous sodium thiosulfate and 15 centimeters cubed of distilled water. And experiment 4. Experiment 2 was repeated using 30 centimeters cubed of aqueous sodium thiosulfate and 20 centimeters cubed of distilled water. And then the 5th experiment, experiment 2, was repeated using 10 centimeters cubed of aqueous sodium thiosulfate and 40 centimeters cubed of distilled water. All right, now what are they asking us? A. Record the volumes of distilled water used in the table. Use the stop clock diagrams to record the results in the table. Okay, so this is just from the description. So the first one with 50 centimeters cubed, there were 0 centimeters cubed of water. And the important thing is as well, do not put centimeters cubed in the table because it's already in the heading. All right, with 40 centimeters cubed, there was 10 centimeters cubed of water. So with 35 centimeters cubed, there was 15 centimeters cubed of water. 30 centimeters cubed was 20 centimeters cubed, and 10 centimeters cubed was 40 centimeters cubed. Always adding up to 50 centimeters cubed to keep it constant. Now let's look at the time taken for the printed words to disappear from view in seconds. So let's look at this stopwatch. Okay, this outer set of gradations, each tick marks 1 second. This inner circle shows the minutes. So each tick here shows 1 minute. Okay, so for this one, 0 minutes, so it's just seconds. So that's 15, 20, 25, 26, 27. So this is 27 seconds. And this one down here, again, no minutes. And this is 30, 31, 32, 33 seconds. So if we look here, again, 0 minutes, and it's 45 seconds. Okay, over here, it's 1 minute and 6 seconds. So that is 66 seconds because it wants it in seconds, not minutes and seconds. All right, and finally, we have minutes. We have 1, 2, 3 minutes and 15, 21 seconds. So 3 minutes and 21 seconds, that is 201 seconds. Okay, so that's 3 times 60 plus 21. Okay, and that equals 201. Okay, B, plot the results from experiments 1 to 5 on the grid. Draw a smooth line graph. Okay, sadly it doesn't all fit on the screen, so I'll have to do it in a couple sections. So if we look at this, the y-axis is the time taken for the words to disappear, and the x-axis is the volume of aqueous sodium thiosulfate used. So looking at the y-axis, each large square is 30 seconds. So the half square, that's 15 seconds. And there's 5 in between there, 5 small squares in between there. So that is 3 seconds per square. Okay, so each square goes up by 3 seconds. And if we look at this, each small square is 1 centimeter cubed. Okay, that's on the x-axis. All right, so I'll just plot those points. Okay, all right, I've plotted my points, and now it's time to draw the smooth line. So it says draw a smooth line graph, and a smooth line graph means do not use a ruler. Okay, all right, so this is actually quite tricky to do. This is why you always do your graphs in pencil, because doing this freehand without a ruler, you tend to do it terribly. Okay, that's really bad. There's bumps, it doesn't hit the lines, so I'm going to just correct that for you. All right, it's not perfect, but it's pretty good. But don't use a ruler if you're drawing a smooth line graph. The other thing that you have to make sure you do is you have to draw little x's. Okay, if you draw a little x and they mark it within half of one of these small squares, so you have to be very careful. If you use a little dot to show your point, you often won't get the marks because the examiner can't necessarily see where the point is. If you want to use a dot, try to make it a reasonable size, but put a circle around it. But a little X is probably the safest way to do it. Okay, C1. From your graph, deduce the time taken for the printed words to disappear from view if experiment 2 were repeated using 20 centimeters cubed of aqueous sodium thiosulfate and 30 centimeters cubed of distilled water. Show clearly on the grid how you worked out your answer. Okay, that's important. Okay, so it wants to know basically what time it will take if you add 20 centimeters cubed of sodium thiosulfate. Okay, so all you have to do is basically read from the graph the time taken here. So to do that, the best way of doing it is to draw a line and draw another line. Okay, so your point that you're reading is right here, and that is at 120 seconds. Okay, now what it says is to show clearly on your graph. So you have to add these lines. If you don't add these lines, you lose a mark. So if you look at this, it's 2 marks. 1 mark is for finding the value. That's 120 seconds. And 1 mark is showing how you did it. Good. Okay, C2. The rate of reaction can be calculated using the equation shown. Okay, so the rate is 1 over the time taken. So calculate the rate of reaction using your answer from C1. Okay, so the time we found in C1 was 120 seconds. So the rate equals 1 divided by 120 seconds, which equals 0.0083 seconds to the minus 1. D1. In which experiment 1, 2, 3, 4, or 5 was the reaction greatest? Okay, let's look at our graph. Okay, experiment 1 was with 50 centimeters cubed of sodium thiosulfate. So this is 2, 3, 4, and 5. Okay, so which one was it the rate the fastest? Well, that was in experiment 1 because the time taken for the printed words to disappear was the smallest. Okay, so that is experiment 1. Okay, D2. Explain in terms of particles why the rate of reaction was greatest in this experiment. All right, so experiment 1 was fastest because there were more thiosulfate particles. The more particles there are, then the more chance that they will collide successfully and react. Okay, Let's write that down. Okay, so there are more thiosulfate particles present in the solution, so that means that there's a greater chance of collisions. And when you have a collision, you're more likely to have the reaction take place. So the more collisions there are, the faster the reaction happens. All right. E. Give the name of a more accurate piece of apparatus for measuring volumes than a measuring cylinder. Well, there are a couple things you can use, but generally the best thing would be a burette. They can be very, very accurate. You can also use a pipette. They work as well. Okay? Measuring cylinders are often have a wider volume. Burettes and pipettes are very, very narrow tubes, so you can measure to very, very precise volumes. F. Suggest the effect on the results of using a 100 centimeter cube conical flask instead of a 250 centimeter cube conical flask. Explain your answer. Okay, so looking at this, you start off with a large conical flask and you decide to use one much smaller. I notice, beautiful conical flask, beautiful. Okay, so you put a little bit of liquid in the bottom of your large conical flask and you wait for and you look down to see when the writing underneath will disappear. Okay, in your other conical flask, that same volume takes up a lot more space. So because you're looking through a larger space here, all the particles are on top of each other rather than spread out farther, it takes a lot less time where you can't see the writing underneath. Okay, so the time would be shorter for the writing to disappear. And this is because the depth of the liquid is greater. So the time would be shorter for writing to disappear because the depth of the liquid is greater. Okay, G. Sketch on the grid the graph you would expect if all of the experiments were repeated at a lower temperature. Clearly label your graph. All right. All right, so if the temperature is lower, then it takes longer for a reaction to take place. Okay, so if it took 30 seconds at 50 centimeters cubed of thiosulfate, then it will probably take longer. So it will be the exact same curve, it will just be slower. All right, so this is my sketch, and it is a sketch of my curve at a lower temperature. So this is my lower temperature curve. All right, and if you notice, it looks pretty much, it should be pretty much exactly the same, maybe not perfect, and it's above the original. Okay, very important. Question 3. 2 substances, solution A and solid B, were analyzed. Okay, so the table below shows tests on solution A. It says some of the tests and observations are shown. All right, so if we go down to the question, identify the gas produced in test 2. And then we have to identify what solution A is. Okay, so let's start out. So solution A was divided into 3 equal portions in 3 test tubes. So the first test, the pH of the first portion of solution A was tested. So pH 1. Ooh, that means it is an acid. Okay, so we know solution A is an acid. All right. Test 2, magnesium ribbon was added to the second portion of solution A. The gas produced was tested. Okay. There was effervescence, which means there was a gas produced, and the gas that was produced did a pop with a lighted splint. Quite often that's called a squeaky pop, and that is a test for hydrogen. Okay, so the gas produced in test 2 was hydrogen. Okay, so dilute nitric acid and aqueous barium nitrate were added to the third portion of solution A. A white precipitate was formed. So the test using nitric acid and aqueous barium nitrate ions, that is to test for the sulfate ion, which means that a white precipitate forms. That means that there's a sulfate ion present. So we know that there's a sulfate ion, it's an acid, and hydrogen gas is produced. What is solution A? Well, solution A is sulfuric acid. Good. All right. Next, tests on solid B. Solid B was zinc carbonate. Okay, well, they're not going to ask you what it is. Complete the expected observations. So dilute nitric acid was added to solid B, and the gas produced was tested. Okay, so the observations. So if for a carbonate, the way to know it's a carbonate is you use lime water. Okay, so you use lime water. You bubble the gas through lime water, and you should see, should turn cloudy or milky or white with white precipitate. Okay, so lime water turns cloudy, or lime water, white precipitate is produced. So that means that it's a carbonate. Okay, the zinc nitrate solution formed in test C was divided into 2 portions in 2 test tubes. Drops of some sodium hydroxide were added to the first portion of the zinc nitrate solution. Okay, for this one, also we get another white precipitate. All right. And then if you add more sodium hydroxide, so an excess of aqueous sodium hydroxide was then added to the mixture, what would you see? So for zinc carbonate, you would expect that white precipitate that it formed initially to disappear, dissolve, goes colorless. So the observation is it goes colorless. Okay, and what's also important, when it says observation, it wants you to write down something you see. It doesn't want you to say carbon dioxide was produced for your part C, for lime water turns cloudy because carbon dioxide was produced. It's not asking for an explanation. It wants you to just to say what you see. That's what you observe. That's very important. You don't get the marks if you don't answer the actual question being asked. So E1, drops of aqueous ammonia were added to the second portion of the zinc nitrate solution. And what observations do you see now? Okay, for this one, you also see a white precipitate. And an excess of aqueous ammonia was then added to the mixture. Again, same thing happens. It dissolves or goes colorless. Question 4. Potassium chloride is a salt that dissolves in water. The solubility of a salt is the mass in grams of the salt that dissolves in 100 centimeters cubed of water at a particular temperature. Plan an investigation to determine the solubility of potassium chloride in water at 40 degrees Celsius. You are provided with potassium chloride and common laboratory apparatus. All right, so there's a few different ways to answer this question. I'm going to only explain one of them rather than go through and explain every single one. Okay, so the method that I'm going to describe involves evaporation. So what is it you're trying to do? Okay, you're trying to figure out the mass in grams that dissolves in 100 centimeters cubed of water at 40 degrees Celsius. Okay, so that's all you're trying to do. So first of all, you need to make sure you measure out a volume of water. A nice easy volume you can use is 100 centimeters cubed. Okay, so you can first of all measure out 100 centimeters cubed of water using a measuring cylinder. If you didn't want to do it with 100 centimeters cubed, maybe you only wanted to try it with 50 centimeters cubed or 20 centimeters cubed. That's okay. You just have to specify how much you're using. And if you're using it with a smaller volume, then you probably want to use either a pipette or a burette. Okay, because they're more accurate for the smaller volumes. And then you just multiply it to figure out how much it would be in 100 centimeters cubed of water. Okay. So the next thing you'd want to do, once you've measured out that water, is you want to make sure it's at 40 degrees Celsius. Okay, so you want to heat the water to 40 degrees Celsius. And you might notice I'm not creating a long convoluted paragraph. I'm just creating bullet points. And that is actually, examiners prefer that. That means that makes it nice and clear and easy for them to see what you're answering. And it keeps it nice and clear in your head. Okay? You only have a certain number of lines. Yes, you can go beyond that, but you don't want to keep going and going and going. You only have a certain amount of time to write your exam. Okay, so bullet points is a good way to go. All right, so the next thing you want to do is add the potassium chloride to that water until you don't get any more dissolving. That would mean there'll be a little bit left over. Just keep adding potassium chloride and stirring, and then adding it and stirring until when you add it, it's not going to dissolve. Okay? Okay, so you want to add the potassium chloride until no more dissolves, and you want to keep stirring it. Okay, then you know that no more is going to dissolve. Just dumping the potassium chloride in and just waiting for it to dissolve, that would take way too long. You need to make sure that it's properly mixed in with the water. Okay, once you've added the potassium chloride and you've kept adding it and you've kept stirring it, and there's a little bit left that just does not dissolve, you want to filter out the potassium chloride that didn't dissolve. Okay, so you want to filter that mixture. And once that mixture is filtered and you have your filtrate, so remember, here's your filter and your little flask. Okay, the stuff at the bottom that drips down, this is called the filtrate. Okay, so you want to take that filtrate and evaporate it so that the water is all gone and you just have the potassium chloride. Okay, so you want to evaporate the filtrate until it is dry. And then finally, you'll have some solid potassium chloride left over. You want to weigh that potassium chloride. Okay, and that will show you how much potassium chloride dissolved in 100 milliliters of water. So you want to weigh the solid. So going through this procedure, you want to measure out 100 centimeters cubed of water using a measuring cylinder. Then you heat that water to 40 degrees Celsius. You add the salt, the potassium chloride, and you keep adding it until it doesn't dissolve anymore. And you keep stirring during that entire process. Then once you've got to the stage where you've dissolved as much as you can in the water, you filter out that mixture. Then you evaporate that filtrate until it is fully dry. And then you weigh what is left behind, and that will show you what the mass in grams of the salt that dissolves in 100 centimeters cubed of water at 40 degrees Celsius is. Okay? So you could even say weigh the solid in grams if you like, but that's probably not necessary. Okay, you need 6 marks, and here there's at least 1, 2, 3, 4, 5, 6. Okay? A couple of these might count as more than 1 mark. All right, so we have reached the end of this paper. I really hope you enjoyed it and found it helpful. If you did, we really appreciate if you like the video and subscribe to our channel. If you have any other questions or anything else you'd like to say, then please leave a comment below and have a great day.